Last time, what did we do? We sort of talked about convex optimization kind of broadly, talked about convex sets and convex functions and what makes a convex optimization problem. And the big deal about convex problems is that essentially we can always solve them. We can always solve them kind of the fixed time budget, super reliable. You always get the global optimum, that kind of thing. So that's really, really good. If you can set up your problem as a convex problem, then you're kind of off and running, and doing convex MPC online works super well if you can do it. And this ends up, we talked a bit about, examples of this. We're going to actually do a couple case studies towards the end of the semester on this stuff to sort of dig deeper, but some really good examples that are, super prevalent in the last 10 years or so. One would be quadrupeds, the sort of standard MIT Cheetah controller is doing convex MPC, solving QPs online. That's how most of the legged robots work. And then the other really big example from the last 10 years would be like the rocket landing problem. So like SpaceX and actually the Mars lander stuff too. These are running convex MPC online as well. And actually both of those we're going to do later in the semester. I'm going to sort of send out the papers, and we'll kind of walk you through the derivations of how exactly those two systems work in practice. There's some fun tricks in both of those. Okay, so today we're going to sort of leave the comfortable sort of confines of convex land and start talking about scary stuff. So we're going to start getting into nonlinear trajectory optimization. Sort of what happens if you can't use a nice linear model for your problem and it's super nonlinear. What do you do? And so this is kind of relaxing those convexity assumptions from last time. And there's basically, I would argue, like roughly speaking, two broad classes of algorithms that are popular for solving nonlinear trajectory optimization problems. They sometimes go by the name direct and indirect methods. I don't love those names. I think they're a little bit misconstrued in the community. But we'll talk about two kind of very, very I would say the most popular examples from each flavor. And we're going to start today by talking about differential dynamic programming, or DDP, which, if you like the direct indirect lingo, this would be, I would say, the most popular, most effective indirect method. So this is, roughly speaking, we saw Pontryagin and shooting. And I argued that Pontryagin is not good, does not work well. You should not do it, really. The way to think about differential dynamic programming is it's basically where the Pontryagin stuff, single shooting stuff we did really early on, was a gradient descent method that was doing shooting. This is a second order method that does shooting. It's a second order shooting method. So roughly you can think of it as like a Newton style shooting method rather than a gradient style shooting method. It still has some of the issues of shooting methods, but it actually fixes a lot of them, and it works quite well in practice. And there's reasons that it's popular. And you can actually push it pretty far. And we'll talk about some of that. Okay, so that's what we're going to do today. This is for short. This is called DDP. It's also called iterative LQR. So who's heard of this before? Not too many, actually. Okay, so this is like a fairly popular algorithm in the robotics community, and I'll show you some cool examples too later on. All right, so yeah, last time we did all this convex stuff, and that was great, but it can't deal with nonlinear dynamics, really. And there's many, many, many circumstances where you have to sort of confront, the nonlinearity of your system. And that's what we're going to do today. And there's kind of lots of ways of getting at this, but I would say the first sort of message from me, which we kind of closed last time, is the linear stuff works really well. And if you can do it, you probably should. Like, if it's good enough for your problem in terms of performance and whatever, you should use the linear stuff if you can. So that's kind of the first message. And I almost every new student who comes and joins my lab wants to do this fancy nonlinear stuff. And usually the answer is be wise, linearize. And if you can do it with a linear model, you probably should. Okay, so that's the first message. The second message from me is that, even if you have a nice convex cost function, like you have a nice quadratic cost, whatever, because we get to make those up. So that can be convex. As soon as you introduce nonlinear dynamics, life gets much, much harder. And it makes the MPC problem non-convex. And sort of all the nice things we had before kind of go away. In particular, we can't really give super strong convergence guarantees or optimality guarantees as soon as we kind of go this route. So that's a little scary. Yeah. Maybe, maybe not. It kind of goes both ways. Depends on the problem. Yeah, I mean, it's usually like a try it kind of situation. So like if you're doing something that's like, I don't know, if you're flying a quadrotor around, and not doing aerobatics, you can get away with a linear model. It's when you sort of start doing barrel rolls and crazy stuff where it's, flipping upside down that you end up needing the nonlinear stuff. Like generally speaking, if you're doing stuff that's kind of slow and, easy, this is like very rough and loose, right? You can often get away with nonlinear models or with linear models. And when you're trying to like you can use linear models for walking, for instance, right? The cheetah controller uses linear model. And I'll show you some examples of that. Actually, yeah, maybe we do that now and have some fun. There's more of this later, but I'll show you I can show you a couple of fun examples, right? So here's just as a teaser, let's see if I can throw this up and you can see it. I need to flip this around. Irritating. This is a single linear model. This is like one A and B matrix for the whole robot's dynamics. That's it, right? So as long as you're where this would break down is if you started to try to do backflips or super parkour crazy stuff where you're really aggressive, right? But if you're just walking around, you can use a linear model, right? So I think that's kind of a rough heuristic is if you're on a nonlinear system and you're not kind of really aggressively pushing the performance limits, you can probably use a linear model. When you're pushing the performance limits, you're getting right up against the actuator constraints and stuff like this, that's when you're going to probably want a more high fidelity model that's really modeling the system so you can push the limits of it, because you got to know where the limits are, right? So I don't know, that's a rough heuristic. But yeah, you can use linear stuff way more often than you think. Here's another fun example. This is a paper we did recently. This is pixels to torques, camera feedback, right? And this is just a single linear feedback policy, super stock, right? So you can do all of the things with a linear model. It's just a question of often performance and how far you can go with it, that you maybe need to start looking at nonlinear stuff. Okay, so that's that story. And I'll say this is caveat, so I'm sort of scaring you here, right? But people do nonlinear MPC all the time, and we'll show you some examples, and it can work really, really well. This is state-of-the-art performance, for instance, on humanoids like Boston Dynamics. They're doing whole body nonlinear MPC. Autonomous driving, pretty much all of the autonomous driving stacks out there are running nonlinear MPC to drive the car and avoid obstacles, right? So it's super common. It does work in practice. The caveat is you're gonna have to work for it. You're gonna have to try harder. You're gonna have to do more tuning. You're gonna have to do Monte Carlo and a bunch of maybe chase down some corner case stuff. You're gonna have to work a little harder, but you can still do it. So I don't want to say that you shouldn't do this. Sometimes you have to do it, but it's a question of it's going to be it's much like convex MPC is basically set and forget. You don't have to think about it, right? It works. It always converges. Here, you're going to have to start playing tricks, and making sure the algorithm is going to converge in a nice way and stabilize your system. We'll talk about some of the tricks. Okay, so that's kind of the overall message. Questions? Yeah. Through the dynamics, nonlinear dynamics. Done. You're non-convex, right? So remember when we talked about convex sets? One way to think about this. So remember convex sets, right? It's you pick 2 points, draw a line, blah, blah, blah. Okay, so when we talk about equality constraints, geometrically, an equality constraint is a submanifold. So if you have linear equality constraints, like linear dynamics, in the giant space of trajectories that we are solving in, that defines a linear subspace, like a hyperplane, right? So obviously hyperplane, if I pick 2 points, connect them with a line, it's going to be on the hyperplane, right? By definition. When I have nonlinear dynamics, that defines a curved manifold. And so if it's a curved manifold, if there's any curvature, I pick 2 points, draw a line between them, it's going to be off that curved surface in general, right? So with equality constraints, to be convex, it has to be linear equalities. That's the only thing that's allowed, right? Because as soon as you have a curved surface, like this doesn't hold anymore, and therefore you get like multiple local optima, all the kind of bad things. This is going back to, remember when we did the like equality constrained optimization example, we had a nice quadratic bowl, and then I put a quadratic equality constraint where it was a like parabolic curve that the solution had to lie on. That thing, you could get stuck, right? Remember, we got stuck on the wrong side, and that's because there was a saddle kind of local optima thing happening, right? So as soon as the equalities are nonlinear and you have these curved solution manifolds, like you're sort of hosed, and bad things can happen. Yeah. Yes. Yeah. So QCQPs can be so general QCQPs are non-convex. QCQP is quadratic objective, which generally we like to be convex, and then quadratic equalities and inequalities. You can have convex quadratic inequalities. That's like staying inside a ball or inside an ellipsoid. That's legal. But if you have a quadratic equality, that means you're on a curved quadratic surface, right? And that's non-convex. So in general, non-convex QCQP is actually a very, very general class of problems that actually encompasses almost all of the optimization problems that we're going to solve in here ever. So any polynomial nonlinear optimization problem can be reformulated as a non-convex QCQP. Fun fact. Also, a lot of like binary mixed integer problems can be formulated as non-convex QCQP. Like if you have binary variables, that's like x squared equals 1, right? Like plus minus 1. So like for a scalar. So quite obviously non-convex QCQP, if it's handling binary variables, that's obviously like NP hard and right. So that's a very general problem class. In general, horrendously hard to solve, like NP hard. So yeah, I don't know. Life is hard. Sorry. Okay. Any other questions about this stuff? Okay, so there are demons in here, but I would say you should know that there's demons and you should be careful. But if your problem's smooth and like generally well behaved, like these things work really well with a little bit of tuning. So you have to know what you're doing. You got to test and whatever, but you can make this stuff work. And there's lots of existence proofs. Okay, so now what I'll kind of like, we're going to write down like a general nonlinear trajectory optimization problem. So this is the stuff we're now going to be talking about solving, and it's a slightly more general version than we were doing before. So in discrete time, we're going to have the x's 1 to n, u's 1 to n minus 1, just like before. But now our cost function, instead of just being quadratic, although I'll say, we still often use quadratic cost functions, we're going to have a more general one-step cost, L sub k, of xk, uk, and then a terminal cost, L sub n, of xn. So that's sort of general cost function. Can be non-convex in general, but often we still use quadratic ones because they're convenient. So generally non-convex cost. And then we're going to have our general nonlinear dynamics. So we'll have like xk plus 1 equals f of xk uk. This more general thing that we've talked about, right? How to deal with those, how to simulate them. So in general, this is nonlinear. And then we'll have sort of general inequality constraints on stuff. So X is in some set, big X, where this doesn't have to be a convex set. And then U is in some general set, big U, that does not have to be convex. So when I write that fancy notation, that's set membership, right? And that just means a bunch of inequalities, right? It means X is inside some set, just means X is subject to some inequality constraints. Could be like obstacle keep out sort of stuff, right? One thing to know, right? As soon as you put a obstacle keep out sort of thing, like if I have a stay out of this cylinder kind of thing, that's non-convex already, right? Because it would be convex if you had to be inside the circle. But if I tell you to stay outside the circle, that's non-convex. So these show up all the time. Even if the, autonomous driving, if you're like, don't hit the other cars, already it's non-convex. So super, super common. Okay, so then, yeah, these are non-convex constraints. Okay, so this is the problem we're looking at. And one note, so this is the general setup. What we're going to assume for now, which we may relax later, we will, is that, and what is standard is we're usually going to assume in most of the derivations and most of the literature on this stuff that the cost functions and the constraint functions are all at least C2 smooth, which means they have at least two continuous derivatives. So I can take first and second derivatives of all of the stuff in here, all the L's, all the F's, blah, blah, blah. So you want to know why I'm making that assumption right now out the gate? So I can do Newton's method, right? I need two derivatives to do Newton's method, usually. Okay, cool. So for now, we're assuming everything's C2. We'll kind of get away from that later when we talk about walking and contact stuff where this is obviously not smooth anymore. And that makes life hard, but you know, there's stuff you can do. Okay, cool. Any questions so far? I'm feeling good? All right, so now we're going to get into this differential dynamic programming idea. And it'll be really familiar, hopefully, because so it also goes by the name iterative LQR or ILQR. And there's subtle difference, but in practice, it's the same thing. And I'll talk about that. But essentially, this is like when I mentioned earlier when we did LQR a bunch, that you could solve almost every control problem with some version of LQR. What this is doing is essentially taking the nonlinear problem, linearizing it about some initial guess, linearizing the dynamics about some initial guess, quadraticizing the cost function around that initial guess, which now you get an LQR problem. And then it's solving the LQR problem basically as a way of getting a Newton step on the nonlinear problem. You take that Newton step, then you relinearize, blah, 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 rinse and repeat. So it's effectively like a sort of a Newton method applied specifically to that trajectory optimization problem, where the sub problems, like each Newton step, is effectively like solving an LQR problem. It's also, you know, you obviously by that definition and the way we saw LQR done 3 or 4 different ways, you can interpret this several different ways. The way we're going to go at it today is to think about it as approximate dynamic programming and kind of derive the step as a dynamic programming thing, just like we did it with LQR. So it looks almost like the DP LQR derivation. So we're going to kind of think about it as approximate dynamic programming. And lots of connections to lots of other things. So we'll maybe talk about some of those. In particular, right, when I say approximate dynamic programming, the approximation part is we're going to basically use a second order Taylor expansion. Of the cost to go. In that DP, like backward recursion, to compute Newton steps on the nonlinear problem. So like one kind of way of talking about this, right? Like here I'm using polynomial function approximators. Like to second order, I get a Newton thing. If I instead were to do this with a deep neural network, like we would be doing, you know, basically actor critic, right? Where you're kind of jointly optimizing a value function and a control policy. So it's the same ideas as the RL stuff. If you use a Taylor expansion, if you use polynomials, it's, you know, DDP. If you use neural networks, it's RL. It's the same stuff. It's like so I think hopefully this is like I like doing it this way first because I think like the ideas are simpler. There's less kind of voodoo and it works simple. It's sort of simpler to implement and converge and all that stuff. So I think like, but yeah, you should have in the back of your mind throughout when we do this stuff that like using a second order Taylor expansion is an arbitrary choice. I could use other function approximaters in here and get other kinds of algorithms. But the key ideas, right, this like dynamic programming stuff, these are very, very general ideas. And you should kind of like, you know, I don't know, I'm trying to show you the basics, but you should think about, you know, ways you could tweak the setup and get other algorithms. And so, yeah, reasons people like DDP in robotics. These have been really popular in the last 10 or 15 years in robotics. Sort of, if you do this right, you can get very fast convergence. And that's obviously nice for online applications if you implement it well, and people have implemented it well and done this and run it online very successfully. And then the other big thing here is it's a shooting method. So I'm doing rollouts. I'm doing a forward rollout in this kind of forward pass. And that means that every iteration of the algorithm is always dynamically feasible. So it's always physically feasible. So I can always go run that trajectory on the robot, even if I haven't fully converged. So this is a big difference between this and like SQP methods, which we're going to talk about later, that enforce the dynamics as equality constraints, where you're not actually obeying the dynamics until convergence. Here, you're always obeying the dynamics, even if the solver hasn't converged yet. So you always have a suboptimal trajectory that you could run on the actuators on the real hardware, which is sometimes a big win for online applications.
That's just if you like run out of time.
Right. If you have a hard, remember, right, I can't tell you how many iterations this is going to take to converge because it's non-convex, right? So basically always when you're doing nonlinear MPC, you're always stopping early because you have a hard real-time budget. So you have so much time, that means you can maybe take a couple iterations. You're never going to solve to convergence. Instead, you're going to have to like take what you've got as best you can after some like, I don't know, 20 milliseconds or something, and stick that on the actuators. So the advantage of the DDP stuff is I can run it 2 or 3 iterations, and whatever comes out of it, it might not be optimal, but it'll be physically plausible, and you could throw it on the robot and it'll work in principle, right? So that's the big advantage of this versus sort of the SQP stuff. People do both, and in general, like I would say labs that do MPC tend to like specialize in one or the other and have like staked out turf on either, there's like DDP labs and SQP labs, and you can make them both work. There's pros and cons to both. This is kind of the pro argument for DDP, that you can have this kind of early stopping and it's still physically real. So this thing, it's working. We'll get into it, but you're doing forward rollouts. It's a shooting method. So I roll out, then I do a backward pass to update the controls. So and then once I've got the new controls, I do a forward rollout again. So because of that forward rollout, I'm rolling it out on the nonlinear dynamics every time. So it's always dynamically feasible. It might be suboptimal, but it's gonna obey the dynamics, right? Okay, any questions about this before we do it? Cool. All right, here we go. So the first kind of move here is, remember our dynamic programming thing, our LQR thing. The kind of core thing in DDP is that we're going to take the general cost to go function and we're just going to expand it to second order. And again, yeah, you could approximate this any way you want, in principle, right? And if you put a neural network in there to approximate this thing, it's Q-learning or actor critic, right? Here it's differential dynamic programming, but like dynamic programming is pervasive in all these things. So here what I'm going to do is I'm going to take Taylor expansion of this guy in delta x. So I've got like a gradient term, and we're going to call that little p. And then I've got a Hessian term that we're going to call big P. And at each time step, we're going to get a little p sub k and a big P sub k. This is essentially exactly the same as LQR. What's the difference between LQR and this? Someone tell me. In LQR, we only had the big P. We didn't have the little p. So LQR, we were always assuming that you were kind of doing this around the origin, is another way to say it. So at the origin, like you're always kind of like that gradient term's 0 always, right? Whereas here, we're trying to like take Newton steps along some trajectory. It's a little bit more general. So here you get an affine term. You get like the linear term and the quadratic term. That's really the only difference between this and the LQR stuff we've already done. Okay, so, and then in general, at time step n, remember at time step n, the cost to go is just the terminal cost, right? So we can bootstrap everything by looking specifically at Pn at the last time step. So little p sub n is just the gradient of the terminal cost. And then big P sub n is just the Hessian of the terminal cost. Okay, so far so good. So that's it. What we're going to do for this particular like derivation for DDP, we're going to do it slightly differently than we did in LQR land. half for notational reasons, half to like force you to get exposed to this. We're going to do this in terms of the action value function or Q function, which we're going to write as S instead of Q because LQR and overloading letters and stuff. But so I think it's healthy to get a little exposure to, the different ideas. So we're going to go that route. I also think the derivation is a little cleaner in terms of the action value, like Q function, instead of the cost to go here. Okay, so I'm going to do this exact same thing now for the action value function, which we're going to call S sub k. And remember, this guy's a function of x and u. So I've got to Taylor expand it in delta x and delta u, sorry. And exact same thing. We're just going to make up some letters for the gradients and Hessians and stuff and use those and basically derive a recursion the same way. So this guy is approximately like the constant s. And then we're going to have a gradient term. So we're going to call that little g sub x for the x part, little g sub u for the u part. And we're going to stack delta x, delta u here. And then the Hessian part, we're going to call it big G. So we're going to have GXX, GXU, GUX, GUU for the different blocks of this guy. And remember, this is a Hessian, so it's got to be symmetric. So in particular, GXU is GUX transpose and vice versa. GUX equals GXU transpose, and GXX, GUU, those other blocks are symmetric, right? All the good stuff. So assuming this, what we're now going to do is just plug this into like the dynamic programming recursion and derive the kind of the equations. It's basically like a beefed up, it's basically Riccati plus those extra affine terms is all this is. So nothing surprising. So here we go. So we can write down v k minus 1 of x, so like the value function or cost to go function at sort of one step back in time. We're going to do min over delta u of this whole thing. So if I write the whole thing in here, we've got x k minus 1 x u, and then I'm plugging in the Taylor expansion, right? So that's constant, drops out. Then I've got the g term, the gradient terms. And I'm going to kind of like write this on multiple lines. So we've got the GXX term. We've got the GUU term. Then I've got the sort of mixed terms. So I've got delta x transpose GXU delta u, and then delta u transpose GUX delta x. So that's the whole thing. And the next move is this thing's a nice convex quadratic thing by assumption. So I'm going to take the gradient set it equals 0 like we did before. This is easy. So I've got now grad respect to delta u of this thing is going to be GU plus GUU delta U plus GUX delta X. And we're just set that to 0. And now I can solve for delta U as a function of delta X and like a constant. I'm just going to rearrange that expression. So in particular, I'm going to get, I'm going to write this down here maybe. Delta U k minus 1 equals minus GUU inverse little GU. So we get a constant term. And then we're going to get minus GUU inverse GUX delta X. And these two terms, unsurprisingly, we're going to call this term that multiplies delta X K. And this is exactly the same K from LQR. So that GUU inverse GUX thing, that's exactly the same expression that we had last time, just written in terms of action value function stuff instead of value function and dynamic stuff like we did last time. So before we had that thing written in terms of Q's and R's and A's and B's. Now we're writing it in terms of this action value thing. Next, we're going to derive what those are in terms of the other stuff. But basically, that term is what we already did before with Riccati. The first term, this constant term, which we're going to call little d, is sort of the new part that's coming from the affine stuff, the linear term, right? So the quadratic term and the value function gave you the feedback term. That's what we had before. That linear term or gradient term is what's giving you this constant. And we'll write this as, in general for us, like another way to talk about this that you'll hear commonly is we've got this minus d k minus 1 minus k minus 1 times delta x. And you'll hear this called like a feed forward term. And this guy, a feedback term. Ugh. Cool. So this is basically it. This is kind of the Bellman backup for this guy, assuming that like second order Taylor expansion stuff. And then we go from here, we just plug this back in to what we had before. Into this to get the new action value function. Or I guess in this case, we were solving the value function. And these are kind of interchangeable, right? So to get vk minus 1 of x plus delta x. So if I do that, I got vk minus 1, x plus delta x is approximately, so we'll kind of, I'll write this in and then we'll do a little simplification. So Taylor expansion-y stuff, we're going to have the kind of one-step cost stuff. Now we're going to plug in, for u, we're going to plug this in. And then we've got kind of all the rest. So this gxx thing. And then just everywhere there was a u, we're plugging this new thing in. So this is the GUU term. I'm going to be like a little shortcut there, if you don't mind. And then we've got the mixed terms where we've got delta x transpose GXU. I'll do the dot dot dots to save some writing. And then dot 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 GUX delta x. So I just plug it back into this thing up here. Wherever there was a delta u, I'm plugging in this definition of delta u that we just got, the optimal one. And then what this is telling you now, if I kind of stare at that and then pick out the big P and the little p from that, I now have pk minus 1 is gxx plus k transpose guu k minus gxu k minus k GUX. So this first line is exactly Riccati. This is the big P. This is what we already had from LQR. The little p is the new part. And, you know, turn the crank, no big deal. What we have up there, it's just me rewriting this stuff kind of in this form. Okay, so that's the whole thing. So now we have kind of a recipe for going back one step in this like Bellman recursion in terms of the action value function. This is like also another way to get at like the LQR thing we did last time. Now we're going to have a little bit of an interlude or aside. So this is how you get this. What we didn't do yet is tell you how to get the G's to begin with. Yeah.
Are G's not time varying then?
They are, yeah. So I'm being a little loose with this stuff. I kind of subscripted them in terms of X's and U's here. These definitely are subscripted. It's like, so SK will have a GK, you know, blah, blah, blah. this is me trying to avoid like an insane soup of sub and superscripts. So what you're always going to do, by the way, is these G's are at a given time step. You're going to like compute these G's along the way to computing these P sub Ks. And then once you got P sub Ks, you can go to the next time step and like from those compute the G's, take the step, get the new P's, blah, blah, blah. So these are sort of an intermediate thing. I'm now going to tell you how to compute those G's at each time step. This is going to require a little interlude on matrix calculus / tensor calculus, where I'll teach you the Kronecker product tricks that I kind of alluded to before in the code. So I think this stuff's, we could skip this. I think it's good for you / kind of somewhat interesting, and just general knowledge stuff that's like kind of fun. So I'm going to show it to you because I think it's useful. But the punchline at the end is maybe you didn't need this stuff, but I'm going to still, I think it's worth knowing about. So we're going to do it. Brief interlude. So we talked a bunch about like derivatives and notation and stuff. So what I'm going to show you now is basically a bunch of tricks involving Kronecker products that essentially let you do all of tensor calculus, like work on third rank, fourth rank tensors without having to do tensor stuff, like just with normal matrices, which is super useful. Where this comes up specifically and why we're talking about it as a teaser, right, is we said we're taking second derivatives of everything in this problem and doing Newton on it in this DDP thing. When I take a second derivative of a dynamics function, that's a third rank tensor. So if I have like xk plus 1 equals f of xk uk, the first derivatives of that are my A and B matrices, which we already saw. If I need to take another derivative of those, that's like taking dA dx, right? And dB dx, et cetera. And so that now, if I take the derivative of a matrix with respect to a vector, that's now a third rank tensor. Think about it like a 3D matrix, right? So that's annoying and a pain to deal with. So I'm going to show you tricks so you don't have to think about tensors, basically. So that's what this is about and why I'm showing it to you. Yeah. Yeah, sorry. Thank you. Yeah, interpret my squiggles liberally, and hopefully, you can actually follow along and interpret the squiggles. I know it's sometimes rough. Okay, so here's the deal. If I have an f of x that's like vector valued function of a vector, so each of vectors spits out a vector. So let's say it's Rn to Rm. So think dynamics function. We're going to now look at the second order Taylor expansion of this. So in the case that m equals 1, i.e. the output is a scalar, so like a cost function. Yeah, did you have a question?
So if you compare the P case, case B,
Mhm.
to what we had with the LQR case, right?
Yeah.
So in the LQR case B, just purely in terms of A's and B's and Q's
And R's, yeah.
So, but here we have these Hessian terms, which basically are like the change of dynamics with regard to X and U, correct? It's like, how do you interpret that?
Okay, so this, I wrote it in terms of this action value Hessian, basically, the big P. It's exactly the same. So if you have linear dynamics and a quadratic cost, the Hessian terms are just, there are no dynamics Hessians, right? The second derivatives of the dynamics in that case are 0. So you just have the cost Hessian stuff. So that's kind of basically what's going to be it. Like literally the big G's in there, they're completely expressible in terms of A, B, Q, and R. And if you go do that, you'll get the stuff we had last time when we did dynamic programming for LQR. It's exactly the same. I just wrote it down in this sort of slightly different notation. There's a reason I did that, and we're going to get into it now. It's because it lets me not think about the tensor crap initially, because it ends up being quite messy. The expressions for the G's are messy when the second derivatives are there. So I'm going to show it to you now. Okay, so in the case m is 1, so this thing outputs a scalar. This looks like a cost function. We already know how to take a second order Taylor expansion of that. So it looks like x plus delta x is approximately f of x plus your gradient, df dx, times delta x, plus something that looks like, delta x transpose d squared f dx squared delta x. So this is, if I pay attention to the dimensions on these things, this guy's R1 by n. It's m by n in general. But if m's 1, it's 1 by n. So that's our gradient vector, row vector. And then this guy is a Hessian. It's n by n for an n-dimensional x, right? But if m is greater than 1, like if we're talking about a dynamics function now that outputs a vector, it's a little different, right? So now I've got f of x plus delta x plus df dx times delta x, where this thing is now a Jacobian matrix. So think like a matrix, right? So this guy's m by n in general. And now this second derivative term is a little messy, right? So one way to think about it is what I have up there where it's this Hessian matrix and it's multiplied by delta x's on both sides and it outputs a scalar. One way to think about this is now when I have to output a vector from this, because it's an n-dimensional vector output, you can think about it as I have slices of, I have like a bunch of those Hessians for each component of the output vector. So you can think about it as like slicing going in the third dimension or something like that, where each output element is sort of, has one of those in it. But like I'm going to write this a slightly different way. So that's kind of the tensor idea. I'm going to write this in a way that's sort of legal with just matrices. And so you can kind of see what we're talking about. Like another way to write this is I take the first term, the gradient term, df dx times delta x, that outputs a vector, right? So that's like a Jacobian vector product. I can take the Jacobian vector product and then diff it again with respect to x. And that's kind of a matrix again, and then I can multiply that again by a delta x. So this expression, you could do that with auto diffing, right? I could write an auto diff expression, and auto diffing toolboxes tend to be good at this kind of like efficiently computing these Jacobian vector product things, right? So you could do that, and that's legal, and that doesn't involve any tensors, right? But it is kind of ugly and messy. And if I were to like, kind of expand this out, that like d squared f dx squared thing is a third rank tensor. Okay, so here's another way to write that thing that plays nice with your normal sort of NumPy, Julia, MATLAB matrix stuff. Also plays nice with auto diffing toolboxes, and plays very nicely with sparse matrix stuff. So here's the tricks. And you can actually do any tensor calculation you ever need to do, basically. You can use these tricks to just do it in terms of normal matrices, which is actually kind of cool and kind of useful, which is why I'm showing it to you. I've gotten a lot of mileage out of these tricks. Okay, so for m greater than 1, this thing is a third rank tensor. You can, as we kind of said, think of this like a 3D matrix. So it has like 3 indices instead of 2, right? And basically, I'm going to now show you some tricks. So one option is to just embrace tensors and like use a library that's good at dealing with tensors. These exist, right? In general, the way you would write this stuff is with Einstein notation, like all the little indices explicitly in there. There is a really good NumPy toolbox called einsum that actually lets you write stuff like that. So you can do that. You can just go all in on tensors. But if you want to stay in matrix land, this is the alternative. So first thing to talk about is the Kronecker product, which I also kind of teased in the code before and some of the examples and mentioned, but I'm now going to like really teach it to you. These are useful in other contexts too. These are really useful for like building big sparse matrices and stuff like that. You can write a bunch of cute one-liners in terms of these guys instead of having to for loop around and index into your matrix. So the Kronecker product of two matrices A and B, and you write it with this circle with an X inside symbol. Oops. That's like unfortunately overloaded with the symbol for convolution. So, beware. I've never had to use both convolutions and Kronecker products in the same paper. So it's never really been an issue where I had to deconflict them, but you should know that that's a thing and it's annoying. Read out loud, the way I say this and the way I hear people say it is A cron B. And if you write this in Julia, MATLAB, Python, whatever, in NumPy, the notation for this is cron, K-R-O-N. So you'd write cron A comma B. is the function call that does this. And it's in all the linear algebra toolboxes. It's a normal linear algebra thing. So this is, let's say this is L by M, and this is N by P. So two different sized, square matrices. This thing is equal to, I take every scalar element of the matrix on the left. So every scalar element of A. So I'd have, for example, A11, and I multiply it by the entire matrix B. So this is like A11 times B, A12 times B, dot, dot, dot. And then like A21 times B, A22 times B, dot, dot, dot. You get the idea. So essentially, I take the entire matrix on the left-hand side and multiply by each scalar element of the matrix on the left and kind of blow this up into a giant matrix. So in general, like this thing, given the dimensions of those guys, this is going to be Ln by MP, right? It's the product of the dimensions of the input matrices. So it builds really big matrices. We used this before, right? When I needed to set up the big QP for solving the LQR problem, I used this to set up the big sparse cost matrices and dynamics constraints for the whole matrix, because there I can make A an identity matrix and I can make B some other matrix, and now I'll get a block sparse matrix, right? So it's super useful for that kind of stuff. So I actually use these all the time in my code. And then the other thing we need to do these things is called the vectorization operator. Operator 1P, I don't know. I can't spell. Okay, so this thing, if I have a matrix A, what this is doing is, if I imagine the matrix A is made up of, column vectors like A1, A2, A3, dot, 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 out to like AM. So let's say A is, this L by M thing. These are now the column vectors, right? Inside A. So what this thing does, we're going to write it as vec of A. And this is also standard in all the usual linear algebra toolboxes and MATLAB and Julia, whatever. So when I write vec of A, this means I take all the columns and I stack them. So I'm going to have A1, A2, A3, dot, dot, dot to AM. Now in this column vector. And so now this is going to be LM by 1. Cool. Really simple. So far, so good. Has anyone seen these two things before? Just curious. Like one person, two people, maybe. Okay. So here's now. So these two things, you got to know these two things. You got cron and you got vec. These are in all the usual places. Okay. So here's like the magic trick that you need to like sort of unlock all the tensor calculus magic. So I'm going to call this the vec trick, because I don't know any other name for it, and that's what I call it. Okay, here we go. So it turns out if I have three matrices A, B, C multiplied together, A times B times C, as long as the dimensions are compatible, right? Whatever dimensions, this is equal to, so if I multiply A times B times C, and that's some matrix, and I take vec of that, so I stack the columns, it turns out this is equal to C transpose cron A times vec of B. This is actually pretty easy to derive if you like stare at it for a sec. It's actually really easy to derive in the block case where you make a couple of those the identity. If you think about what it's doing, it's not too hard to like convince yourself that that's true. And in particular, there's special cases of this that are extremely useful. So if I have, for instance, vec of just A times B, what you're going to do in this kind of situation is pretend there's an identity on one side or the other of that expression. So I can write that thing as either B transpose cron I times vec of A. Maybe that's a terrible A. Or I could go the other way and write it as I cron A times vec of B, right? Everyone see that? Okay, so yeah, like those special cases where it's just an A and a B, it's really obvious actually that this is correct if you stare at it. If you basically write down the Kronecker product, it's sort of really obvious what it's doing. It's like taking like the sort of, look at the icron A times vec B1. Literally, if you think about what matrix multiplication is doing in terms of the column vectors, right? If I do A times B, it's taking A times each column of B, right? So what this thing is doing is stacking all the columns of B into a vector, and then it's taking A and making a block diagonal concatenation of the A's such that each of those is hitting each equivalent column in the stacked vec, right? So that's sort of obvious. So the more general case is like, if you kind of understand that, you can convince yourself that the three matrix one holds up too. It's pretty easy. Okay, so why do I care about this? This is the magic trick for differentiating matrix expressions. So if I want to diff a matrix with respect to some vector argument, I just vectorize the matrix. So I'll show you what I mean by that. So let's say I have a matrix A that's a function of a vector X. Specifically, what I'm talking about here is if I have a dynamics function f of X, I linearize it and I get A. That A is also a function of X, right? So if I linearize in a different spot, a different X, I'll get a different A. So think about A as a function of X. So if I want dA dx, if I write this sort of thing, and so this is literally when I want the second derivative of my dynamics model, this thing is equal, I can write this as just d vec of A dx, and now this thing is just a matrix, right? So if I do vec of A, I get a big column vector. I know how to diff column vectors with respect to column vectors. It's a Jacobian matrix, so that checks out. And this thing now is going to be based on the dimensions we had, right? Lm, if A is sort of L by M, this is going to be L times M by N, if X is n-dimensional. And what we're going to do now is kind of like overload notation a little bit. And we're going to say in here for us, anytime I write dA dx for like any matrix A, the vec is implied. So we're always going to do this. Whenever I take a derivative of a matrix, you're always just going to like assume it's vectorized. And hey, if you follow the conventions and do the other things we talked about, chain rule still works. Life is good. You can just kind of keep trucking and do all the usual stuff. So anytime I diff a matrix, there's sort of an assumed vec in there. Okay, everyone cool with these ideas? Okay, so now we're gonna like go back to Taylor expansion of that f of x. So I've got f of x plus delta x, assuming everything's vectors, right? Like i.e. dynamics function. I've got f of x plus df dx times delta x, which is A times delta x, right? This is our A matrix. And then the Hessian term, maybe I'll just write it down and then we'll like kind of stare at it for a sec. This is going to be 1/2 delta x transpose cron I d squared f dx squared delta x. And to be super clear, right, this thing is dA dx, which for us, right, is d vec of A dx. And to get from here to here, what I literally did is I did d dx of vec of I times A of x times delta x. So I basically took the expression for A times delta x and diffed it again with respect to delta x. So I like sort of assume there's an identity there. I just take this whole thing, I do the vec trick, I pretend there's an identity on the left, and then I get, I use the ABC vec trick, and then I get the thing on the right. And in particular, though, this gives me a clean definition of that dynamics Hessian thing, right? It's d vec of A times dx, right? Like that's what we're doing. And this is like how you get it, and that's it. So I now know how to take second derivatives of dynamics functions. I don't have to do third rank tensor stuff. I can code this up. I can do this with Ford, Diff, and Julia. super easy, right? I write a function that computes A, and then I just do the vec thing and call it for diff again. I get this thing. Everyone cool with that? Okay. Last trick that we need to do this, which is sometimes, and by sometimes I mean we will imminently, we need to diff through a transpose. So if you have the ABC expression and like say it's B transpose in there instead of B, so I have to like diff through the transpose, then you need one extra trick. And basically what we need to do there is think about what the vec of the transpose is. I can't write. We need to diff through a transpose. And that's going to look like, for example, ddx of like A of x transpose B. So this is equal to, right, B transpose cron I vec of A transpose, right? And so what I'm going to do right now is we're going to define a matrix. We're going to call it capital T that literally maps, and I'll write this, dA dx. This is defined such that T times vec of A equals vec of A transpose. So it's basically a permutation matrix that's going to permute the vec of A to look like vec of A transpose. You can figure this out and write it down. There's a toolbox for it. I wrote matrixcalculus.jl, which is up. You can install it. That has all these things in it. There's a MATLAB one too. So here you go. This thing is called the commutator matrix. Fun fact. Okay, that's all the stuff you need. Now you can do all of tensor calculus without leaving the comforts of NumPy. Hooray. Any questions about this stuff? Cool. I don't know. This is arguably not that useful in your life, but I think it's good to know that it exists in case you ever run into a tensor. Now you don't have to be afraid, you know? Okay, here we go. So now to finish off our whole discussion, we can Taylor expand the action value function. And so specifically, we've got s at time k, function of xu. This thing is specifically, right, it's the one-step cost at time k plus the value function at the next time step with the dynamics plugged in. Right? Remember this from our dynamic programming discussion. It's the definition of action value function. And literally all I'm going to do now is chain rule this and take first and second derivatives. That's it. Right? That's all we're doing. The reason we had this whole interlude on this thing is so I can take the second derivatives of this. Okay, so first derivatives we know how to do. That's easy. So we got ds dx is just partial L partial x plus, I'm going to write it as dv df dx. Cool. And this is, as we all know, right, df dx, this is just our A matrix. And then that's, you know, grad v, right? The other thing. And so this tells me this is what little g is, right? This is little g sub x is grad x of the one-step cost plus A sub k transpose little p k plus 1. Everybody good with that? I'm just writing it using the kind of the column vector notation and whatever. I guess this is LK. I want to put the time steps on there. Okay, then I can do the same thing for the u's. So it's ds du. It's partial L partial u plus partial v partial f df du. And so this is the B matrix, obviously. Everything else should be kind of obvious. So this is little g sub u, and it's grad with respect to u of L plus bk transpose pk plus 1. Okay, those are the gradients. Easy. We know how to do that. Now I'm going to write you down the Hessian terms. They're a little gross. It's super straightforward. I'm literally just chain ruling. So I'm taking the little g's, and I'm just taking another set of derivatives with respect to x and u. Nothing magic, right? So I'm just going to write it down to like spare us having to like sit through that. You can go back and do it yourself. So this is partial, this gxx is partial g sub little g sub x partial x. I'm just taking another derivative with respect to x. And it's going to end up being Hessian with respect to x of the one-step cost. And then if I stare at this, right, so little g sub x, I'm going to take that thing's derivative with respect to x. So the first term, I just get another derivative of L. That's easy. The second term, if I diff little p with, I have a product rule there. I have like a times p. So if I keep the a fixed and then do dp dx, dp dx is big P, right? That's the gradient. So if I take another derivative with respect to x, I get the Hessian. Cool. And so that's going to end up looking like so. And this should look very familiar because this is exactly what this looks like in the standard LQR derivation that we did already, right? Okay, and now I'm going to do, going back to that product rule thing, right? I did the dp dx. Now I have to do dA dx, right? I have to do the other x, the other term in the product. So I'm going to hold little p constant, and I'm going to diff a with respect to x. And that's where the tensor crap comes up. So here we go. That ends up being little p, k plus 1, cron I. Because it's a transpose, I get that commutator matrix. So that's the T. And then I get dA dx. So this is just plug and chug, nothing magic, right? It's using the recipe. I'm just doing the chain rule. Okay, so now I'll just write the other ones down without being, belaboring it too much. This is now GUU, so this is little g sub u with respect to u. Unsurprisingly, Hessian with respect to u of the one-step cost. And then I'm going to get B transpose big P B, again, exactly the same stuff. And then this Hessian of the dynamics type term looks like the following. Like, it looks almost the same. It's just now dB du. Cool. And then there's one left, which is the cross term. So this is GXU. And I could do this two different ways, right? I could do little g sub x respect to u, or I could do little g sub u respect to x. And I get the same answer. Why? Hessian symmetric. Another way of saying that is equality of mixed partials from like your vector calculus class, right? Like from freshman year or whatever. That equality of mixed partials thing is why the Hessian symmetric, by the way. Those are the same statement, if that wasn't clear. Okay, so partial, I'll do it this way. Partial g sub x, partial u. You'll get the same answer either way. So this is now del xu of the one-step cost. And then A transpose P k plus 1 B, or it's A k B k. And then the tensor term, we're going to get the following thing. This is u. Okay, that's the whole thing. So now you know how to compute the g's at each time step. And then you have the recipe for taking those g's and doing the Bellman thing to get back to like, to get the delta u's and the big P and the little p. So that's the whole recipe. Okay, any questions about this? Yeah.
We said that our big G of XU is going to be the transpose of the UX, so this is also a symmetric matrix, is what you're saying, right?
No, GXU is not symmetric. The whole Hessian's symmetric. So specifically GXX, GU are the blocks on the diagonal. Those two are symmetric. The whole Hessian's got to be symmetric, which means GXU equals GUX transpose. So that's the symmetry argument there. But GXU itself is not symmetric. That make sense? Yeah, if you go back and look at the way back now, I guess, yeah, this whole thing has to be symmetric, right? So that means the diagonal blocks have to be symmetric, but those off diagonal blocks, they need to be each other's transpose, but each one on its own is not symmetric. Cool.
Yeah, you're saying like we could do it in either way.
I'm saying you could compute either one, right? Which means you could do the mixed partials in either order, and you'll get the same. You'll get one of the other transpose, right? It's like it's the same thing, so you could do it either way. I chose one way. You could do it the other way. Blah blah blah. Okay, cool. Any other questions about this?
Why is the T subscripts K?
Because it's the cost to go at the next time step in the Bellman recursion, right? I take VK plus 1, I plug in F, and then I'm like in this backup thing, right? So let's see, cost to go expansion. Yeah, so when I do this, I'm solving for VK minus 1. Inside there, I've got the K terms, or if I'm solving for VK, here's maybe the better way. The definition of like the, the action value function thing, right, too, is kind of tells you what's up as well. Where'd that go? In the Bellman backup, I'm like now trying to, scrolling on this is surprisingly annoying. This stuff is kind of showing it. And then like, where did I write the action value definition? Yeah, sorry, because I'm zoomed in super far on this, I can't actually see stuff super well when I'm scrolling. But yeah, okay, that. So yeah, you get the idea. So the action value function at time k, by definition, is like the one-step cost of time k, and then it's the cost to go at the next time step with the dynamics plugged into it, which what that's doing is basically like, you can think that composed function is basically like time reversing, like it's sort of, you can think about it as it's mapping VK plus 1 backward in time, a time step, right? And then you've got to add on the cost for this time step. Does that make sense? So yeah, there's some subtlety in the time steps. Yeah. Everyone cool? Okay, so now we get to do it. And hopefully I have some other fun stuff to show you too. So this is incredibly annoying. Okay, where is stuff I actually want? Okay, here we go. Cool. So this is, we're going to do this on the Acrobot. Has anyone heard of the Acrobot before? Okay, so Acrobot is a double pendulum so it's 2 degrees of freedom, right? It's got a shoulder joint and an elbow joint, but it only has one motor. It has a motor only at the elbow joint, so it has a passive shoulder. So double pendulum with only an actuator here. So it can do this, but it can't exert any torque here. The reason it's called the Acrobot is it's a like low dimensional simple toy model for an acrobat on a trapeze. So the idea is an acrobat on a trapeze. You can bend at your waist to get a whole bunch to do swinging and stuff, but you have very weak wrists. So you basically can't exert much torque with your wrist. It's all coming from your waist, right? So that's the model. Think about an acrobat on a trapeze. So let's see, this is all setup stuff. These are the dynamics. I'm giving them to you. Like, this is kind of gnarly. I don't expect you to derive this. So the derivation of this is a classic problem in like most sort of grad level dynamics courses. You can like write the Lagrangian down for this and kind of turn the crank and get it pretty easily. This is, ultimately this is just the manipulator dynamics. You can use a toolbox for this too. I'm just doing it here because we have it. And I think we put a little friction in there, whatever, not important. We're using RK4 to discretize like always. What the hell? Cool. What else? And then here's the A and B matrices. I'm using 4diff to get them, just 4diff right through the Runge-Kutta to get the discrete time A's and B's directly. That's cool. Then this is just some setup stuff. So I'm going at 20 Hertz, 10 seconds, whatever. This is all kind of fine. Cost function, Q's and R's, quadratic costs, like the usual thing. Specifically though, what I'm doing here is I have an X goal, and the X goal, so I'm going to start it down here, and I'm going to make the goal state the upright equilibrium. So I'm trying to do a swing up of this guy. So it's going to have to like pump and try to swing itself up and balance at the top. So that X goal is the upright equilibrium. And otherwise, yeah, just Q's and R's, like standard stuff. The one thing that's different here is I have a big QN. And the idea there is I don't care so much about the cost during the swing, but I care a lot about it getting to the desired goal state at the final time, right? So I make the QN really big. And that's that. Cost function, whatever, stage cost, terminal cost, full cost function, that's all good. Okay, so initial guess. What I'm going to do here is X naught is downward, and then X goal is upward. And then I'm initialize the X trajectory with all zeros, so like just hanging down, whatever, it doesn't matter. Actually, it really doesn't matter because I'm doing a rollout at each step of this guy, which will become clear in a sec. And so that's that. And then the U's, this is actually somewhat important. I'm actually going to initialize the U's with a little bit of random noise. It turns out that helps. The reason it helps is if I'm just doing this, and I initialize everything to 0, because of symmetries in the problem, like it turns out there's a whole bunch of gradient stuff that's 0 at the bottom. And without any noise or anything in there, it can't decide whether to go swing up left or right. There's because of the symmetry. So having a little bit noise breaks that symmetry and kind of gets it in a good spot such that like the gradient information is nice and it works out. Okay, so there's that. I'm going to start by just rolling this out with the noise, which doesn't do anything exciting. Actually, I can animate that if you want. We'll do this in a sec, but let's try it to make sure this works. Cool. So it's just wiggling around a tiny, tiny bit, not doing much of anything. This is annoying. Okay, cool. So you get the idea. All right, so that's that. Then here's the meat. So we're going to roll it out. Then here's the DDP algorithm. I'm like sort of making up. So I got the big P, the little p, the feed forward is the little d, and then the feedback is the k. So here's kind of, and then here's all the g's, right, that I'm going to use. I don't need the g's. I don't cache the g's. I just compute them at each time step, which is why I didn't like index them with respect to k, which came up earlier. And then I have a termination condition here, which is that the feed forward little d's, once they get tiny, I stop basically. Then kind of here's the backward pass is exactly what we just derived. Yeah, I don't know. That's what it is. And so here's the rub. Remember we had all that tensor stuff? Is any of that here? So I dropped all those second order dynamics terms here, the tensor terms. The story here is basically including those terms, that's doing Newton's method. That's full second order, right? If I drop the second order derivatives of the constraints, i.e. the dynamics constraints here, what is that called? Does anyone remember from when we did optimization at the beginning? Gauss-Newton, right? So I spent all this time teaching about tensors and everything. And then when we actually do it, we're just going to ignore those terms and do Gauss-Newton. So full Newton is when you include those terms. Gauss-Newton is when you throw them out. Remember the whole conversation around like wall clock time and, you know, so if you can try it both ways, and I actually commented out and then I ended up deleting it. You can compute those terms of forward diff. It's easy, but it turns out it's slow. This is like 10x faster without them. You could implement those efficiently if you tried hard, but in the end, it's just not worth it, and nobody does it. So officially, ILQR is the Gauss-Newton version, and DDP is the full Newton version. If you go back to the original papers, in practice, people use those terms interchangeably, and they almost always do the Gauss-Newton version in practice. So this is what is standard, and you will see. I don't know. That's what it is. So this is the backward pass. And then once you do the backward pass, you get the feed forward and the feedback terms. You then do a rollout on the full nonlinear dynamics, where you plug in those new terms. And in particular, we're doing a line search. We're doing our MIHO just like we've done in the past, where I have the alpha on that feed forward term. And I'm doing standard MIHO line search stuff, which is down here. So I roll it out with the corrections on the U's through the full dynamics. And then I'm going to do a line search on the alpha with this MIHO condition, like we've seen before. And then I'm printing a bunch of stuff so you can watch the convergence and all that good stuff. There it goes. So yeah, here we go. We're going to solve it. Takes like 300-ish iterations. And what comes out is this cool looking like double pump move. So this is the U's. These are the angles, the joint angles. And then we can like animate this and watch it. Pretty slick. So this is a pretty benign problem. This works every time. It's super reliable. Like it has a random seed in there for the U's. If you run this though over and over again, you'll get the exact same answer every time, no matter what the seed is. And that's because it's like a pretty easy problem. If you play with this, I highly recommend playing with the time horizon and the costs. If you make the R really big, you'll get versions of this with more pumps, where it'll like pump 3 or 4 times instead of twice to get up because the control cost is higher. So if you stretch the time horizon and crank up R, you'll get stuff with more pumps. It's kind of fun. So any questions about, you should play with this. It's super fun. This works well. Yeah.
It's easier to shift the Acrobot to vertical position from somewhere.
Maybe, I don't know. I mean, in general, this is non-convex. You need an initial guess, but I just showed you it's a crap initial guess and it works really well.
All we need is to pump in energy inside the Acrobot to push it up. So
There's other ways you can solve this problem for sure. There's so-called energy shaping techniques where you pump energy in. Those though don't always work, and this works really well. I now want to show you something. It's time to go, but this is how far you can push this. This is results from our lab from like the last couple of weeks. This is literally what I just showed you, the most dumb stock vanilla ILQR, nothing fancy, running on top of Mujoko. So it's just using the Mujoko dynamics, the Mujoko Jacobians. Running on hardware. Let me start it over again because it face plants. This is pretty fresh, but check it out. This is like, there's no training, nothing. Real-time ILQR on top of the Mujoko. It's pretty sick, right? And obviously it kind of face plants, but this is like literally what I just showed you with nothing fancy. It's like literally you throw this in Mujoko. If you can get the implementation to run fast enough, you can just do this on hardware. I'll show you another one where it's the exact same code. It's just, different behavior. We're doing like bipedal walking. And again, like there's no training. It's all real time. This is online behavior synthesis, right? It's just like learning how to walk. There's nothing fancy. Like you could code this up from what I just showed you. Like you take the code that I just gave you, plug in this in Mujoko, like you could do this on hardware. Pretty slick. We're publishing it soon. The thing on the left is that there's a GUI Mujoko where this is integrated. So this came out a year or two ago. It's called MJPCs. One of my former students did it, but we put it on hardware, which hadn't been done before. But yeah, this is all like, again, all just real time. It's all just working. The secret sauce for why this is happening is that Mujoko uses a smooth contact model that smooths out all the non-smooth contact dynamic stuff. So the gradients are nice, and you can just run vanilla on keyboard on top of it and get stuff like this to happen. Yeah. I'll leave you with this. Yeah, yeah. I mean, that's kind of what the first video was. The first video is it getting up from. Anyway, thanks, guys. Catch you next time.
In this society,